You are welcome in ECE 303 receivers, antennas and signals from University of Kufa. The first topic of this course will be transmission lines. A transmission line is a structure that transfers or guides the electromagnetic energy from a point to another point. And there are different forms or shapes of transmission lines. So it could be as a two parallel wires or coaxial cables, or microstrip line like in printed circuit board, or fibers, optical fiber, or waveguides, and go on. But in general, transmission lines could be classified in two types according to the spatial distribution of energy inside it. So, in general, all the two conductor transmission lines, okay, where the electric field is orthogonal or the magnetic field, and both of them are orthogonal on the propagation direction. So this transmission line is called transverse electric magnetic transmission line, because the energy will be distributed in a single mode, in a single shape, where all the electric field orthogonal on all the magnetic field, and both of them, all the component of the electric field, all the component of the magnetic field, orthogonal or normal on the propagation direction. Otherwise, examples for this like coaxial cable or two parallel wire or two plate line or coplanar waveguide, strip line, and go on. Otherwise, like optical fiber or waveguide, where the spatial distribution of the energy will take different shapes or different mode. So we call this type of transmission lines as a higher order transmission lines. So we have TEM transmission lines, or transverse electric magnetic transmission line, where this type of transmission line, it has single or fundamental mode. The energy inside this type of transmission line will be propagated in a fundamental mode, in a single mode. So the energy will be distributed where all the electric field orthogonal on the direction of the propagation, and also all the magnetic field orthogonal on the direction of the propagation, and both of them orthogonal on each other. Okay. The other type of the transmission line, where the energy will be distributed with higher order modes, with different modes, okay, because the electric field or the magnetic field is not absolute orthogonal on the direction of the propagation. An example of the TEM mode transmission line, the coaxial cable. We could note here the electric field line in red is radial orthogonal on the magnetic field blue in green, and both of them orthogonal on the direction of the propagation, inward or outward the page. So here we have two conductor transmission line, the coaxial cable, and inside it the energy spatially distributed in a fundamental mode, in a single mode, where all the electric and magnetic fields are orthogonal on the direction of the propagation. So we said one shape, or the shape or one type of the transmission line is the two parallel wire. So if we use any two parallel wire connected with source of voltage or current and loaded by RC or RL, so could we consider this as a transmission line? Yes, it could be. Okay, so why previously, like in electric or electronic circuit analysis, we ignored the effect of this wire or this interconnect, okay, in our analysis? So the answer is, previously we ignored the effect of the interconnect or of this wire because the relation between the applied of the electrical signal, and specifically the relation between the length of the applied of the signal or the frequency of the applied signal to the length of the transmission line or the wire itself. So previously we worked with electric signal oscillated with very low frequency. So its frequency may not exceed 60 hertz, and according to that it has very long wavelength. So by compare its wavelength to the length of the transmission line or the length of the wire, so this length, it could be neglected by compare it with the length of the wavelength. Okay, so if we take this ratio, the length L of the transmission line or of the pair of wire, and compare it with lambda, and lambda is the wavelength of the applied signal. So if we are talking about electric signal oscillated with 60 hertz, so lambda will be very low compared with L. So this ratio will be smaller than 0.01, and according to that the variation of the electric signal, the variation of the voltage or the current or the electromagnetic wave along this length, okay, of the transmission line, it could be neglected. So it could be considered as a DC signal, okay, in term of the space, the distance. Okay, so now we are talking about signal with high frequency, so we expect the length of the wavelength or the wavelength, sorry, of the applied of such signal with high frequency will be short, okay, and it will be in the same order of the length of the transmission line. So according to that, we expect the ratio between the length of the transmission line and the wavelength of the applied signal is equal or larger than 0.01. So according to that, okay, because this comparison between L and lambda, between length and wavelength, so the effect of the transmission line will be apparent, okay, and it's very difficult to ignore this effect in such high frequencies. So example of these effects, first the delays. So now if we applied an electric signal with voltage, its amplitude is equal 1, okay, and its frequency 1 kilohertz, okay. So if this electric signal, if this voltage is applied across the point A to A dash, and it's traveled to reach to the point B to the B dash, okay, so between these 2 points, if we use a transmission line with length 5 centimeter. Okay, so the voltage at point P to the B dash, if we calculate this voltage, it will equal 0.9999, so it's very close to the primary voltage 1. Okay, so we could consider the voltage is keep constant, and the length of the effect of the length of this transmission line is ignored. Okay, this length, okay, is ignored, and the time to travel the signal from A to A dash to the B to the B dash is very short, so it could be ignored, and there is no delay between the traveling or between applied the voltage across this point and its appearance across this point. Okay, but if we apply same signal with amplitude 1 and frequency 1 kilohertz, okay, if we apply on the transmission line with length 20 kilometer, so this signal will be traveled and reach to the point P to the B dash, and if we calculated this voltage on we calculate this voltage on B to the B dash, it will be 0.9. So now the length of the transmission line, okay, it has effects, because if this length cues delay, okay, between the voltage across A to A dash to the voltage which reach to the B dash. Okay, so this delay or this length cues delay, okay, to the traveled signal between A to A dash, and that's because now we have length of transmission line 20 kilometer, so it could be close or in the same order of the wavelength of the applied signal 1 kilohertz. Okay, the other effects of the transmission line is the dispersion. The dispersion, that means the signal will be distorted through its travel through the transmission line. So when the transmission line or when electromagnetic wave or electric signal with different frequency traveled through a transmission line, okay, in dispersionless line, that means all the component of this electric signal will be traveled at the same velocity. So the velocity of the traveling inside the transmission line is independent of the frequency of the applied signal, and according to that all this component will be traveled at the same velocity and reach at the same time. But in dispersive line, okay, the components or the traveling velocity through the transmission line will be dependent on the frequency of the applied signal. So the signals with high frequency will be traveled fast from the other component with the low frequency, and according to that some component will be reached faster than the other component, and because that the signal will be distorted, okay, will be stretched on and get more broadening with time, because part of the signal reach faster than the other part. Okay, and that's because the dispersion effect of the transmission line. Also the other effects in the transmission line is the reflection. So because this transmission line or this two parallel wire, it will have a reactance part, reactance effect, okay, so could be work as a capacitor or as an inductor. So some part or some energy will be stored inside the transmission line and then traveled in the opposite direction of the traveling direction. So according to that, there will be some energy of the signal will be reflected in the opposite direction. That's because with high frequency electrical signal, this two parallel wire does not look like just two parallel wire. So it works as a resistance and reactance part, reactance elements like capacitors and inductors. And according to that, according to the behavior of the capacitor and the inductor, we know these two bars will store the energy inside them and then launch this energy. So it could be traveled according to their value, it could be traveled in the opposite direction and cause the reflection phenomena. So the effects of the transmission line: first, the attenuation, of course, even if it's just wire, because it's this transmission line is made of conductor, so it will has a specific amount of the attenuation. Second, the delay. Third, the dispersion. And fourth, the reflection of the signal or part of the signal in the opposite side. So according to that, we could imagine or we could specify the model of the transmission line. The transmission line here is not just parallel wire, okay, or two wire in parallel. So according to that, the transmission line look like a series or a consequence of RLC circuit. Okay, the transmission line itself is made of conductor, so according to that, it has a significant amount of the resistance to the applied current. Okay, because the high frequency, these two parallel wires will be look like an inductor for the applied signal. So there will be effect in this transmission line look like the inductor effect. And these two parallel wires look like a capacitor, it look like a two plate, okay, for the applied or for the high frequency applied signal. So there will be effect of the capacitor, okay, in this transmission line, beside the attenuation which is caused by the dielectric material between these two parallel wire, which is represented by the conductance, okay, amount of the conductance. Transmission line with a significant length could be modeled or represented by a multi-stage or consequence of a RLC circuit in series. So cause that the applied signal will suffer from attenuated by the conductor and the dielectric material. This is the first phenomenon. Okay, it will be delayed by the reactance part, because the signal now will be charged in the capacitor and recharged, charged and recharged, and some of the signal will be stored inside this reactance part, so the traveling will be delayed, okay, inside the transmission line because the effect of the reactance part. Okay, in real there is, of course, you know, in real there is no reactance part, but there are their effects. Okay, this two wire works as inductor and capacitor. Okay, so again, the applied signal will be attenuated by R, will be delayed because the existence of L and C. Also will be, it could be reflected because the existence or the effect of L and C. some of this signal, okay, or maybe all of it will be propagate in the opposite side, and that's what we call reflection. So now if we need to calculate or to follow the current or the voltage across this transmission line, we need to model the transmission line look like a consequence of a RLC circuit or lumped element circuit as shown here in the slides. So here we have R dash, L dash and G dash on all of this. That's mean the resistance per unit length, and so all this value R dash, L dash, this is calculated for this section with length delta Z. So this is ohm per unit length, this is Henry per unit length, and this is Farad per unit length, and this is Siemens per unit length. And the calculation of the R dash, L or J dash or C dash, its calculation is different according to the type of the transmission line. So according to this table, you could see how we calculate R dash, which is, as we said, resistance per unit length. So it's different in coaxial or in two wire or parallel plate, and same for the other parameter. Okay, next we will talk about how we calculate or how we model the propagation of the electric signal or of the electromagnetic signal inside the transmission line. Of course, here we are talking about electrical signal. The electromagnetic wave here will appear as electrical signal, so we will deal with voltage and current instead of electric field and magnetic field, and we will work with resistance and inductance, conductance and capacitance instead of permeability, permittivity and conductivity. Okay, see you.